let me turn it over to Joe. He's a student I met virtually, I guess, from University of Utah. So we'll just leave it to that. Joe said anytime you have a question, feel free just to unmute yourself and shout it out. Other than that, Joe, it's all yours. Thanks for coming by today, too.
Yeah, no problem. Thanks for having me. So, hi, everyone. My name is Joseph Lyman. I'm an undergraduate student at the University of Utah. I will be going into my 5th and final year, that is if I survive this summer, studying electrical engineering at the University of Utah. And for the majority of my studies, I've been interested in semiconductor materials and devices made from these materials, and kind of in addition to all this, the whole quantum world, quantum computing, so on. And what I wanted to do today was give anyone of any background sort of a working knowledge of semiconductors and this quantum well, which is a very basic quantum structure that you can fabricate using semiconductor materials. And I just want everyone to be able to understand how they all relate together and are useful for society, how we use them in different applications. But actually, before I talk about anything, I think that I am obligated with this many people listening to my voice to make a quick comment on what is happening around the globe. And I'm talking about massive protests against racial inequality. And I don't want to make it political or personal or anything, but I do want to make it scientific. And I just want to say that as soon as you have a society that suppresses one part of itself, it suppresses the whole society. And racism itself is a cancer to humanity. It's a cancer to science. In order to truly maximize our potential to discover and innovate, we need unbiased influx of minds and ideas. And so I would encourage all of us as people who are interested in STEM field to have this quantitative mindset and a unique problem-solving ability to solve problems, to approach this problem in a novel way. So I think that means picking up some papers about community-based solutions of crime and drug addiction, mental illness, and crunch the numbers for yourself and sort of investigate, what does this mean for my community and what does this mean for science? You know, if you can cut savings in, you know, your community's budget and put those funds towards education, towards transportation and housing, how could that benefit science? How could that bring in more minds and more ideas to advance this field that we're all interested in? So that's all I wanted to say about this. I would just encourage everyone at this time to kind of think outside of the box, you know, see a bigger picture and how you fit in and how you personally have a unique skill set that can contribute to make change. And so with that, I'm going to flip my camera around. I've got this jerry-rigged document camera. It's literally just a plank of wood across 2 stacks of speakers, and we're all about it.
Excuse me. So, folks, I think if you double-click Joe's camera, I think it will go to full screen. Correct me if I'm wrong. Anybody who's got a better trick.
So yeah, can everyone see this whiteboard? And I hope.
I see it. Okay, yeah, I can see it perfectly. So the trick is put your mouse over Joe's video and then right click, and I forget what it says, but because I already did it. Anybody? It's called, I think it's called Spotlight Video or something, and you'll be able to get. It's coming in very clear. Man, your camera's good.
That's that cell phone, I guess. My laptop would be much worse.
Oh, okay. So what we're seeing, though, Joe, is we see to item 5, gallium. So yeah, I think for me anyway, it looks perfect now. You're
all
good.
Right, well,
sometimes the menu bar will pop up and crop the bottom, but I think you're all good. It looks good.
All right. So here's just an outline of what I'll be talking about today. First, I want to go over just very basic background about some of the words I'll be using and some of the concepts I'll be bringing in, and just make sure that we're all at a baseline on the same page from the beginning. And then I want to talk about semiconductors, what they really are, and in reality, why we're even talking about them. How are they useful? Then I'll use, from talking about semiconductors, talk about how you create a quantum well using only semiconductor materials, and kind of highlight some of the quantum behaviors of the quantum well. And then I'll talk about how you use a quantum well to design a photodetector. And then I'll briefly talk about my own research that I've been involved in, and that is exploring gallium oxide, which is an emerging semiconductor material that is being researched actively in present times, and how it stands to improve the performance of these devices. So first of all, let's talk about this vocabulary. So when I talk about elements, I'm guessing that everyone knows what I'm talking about. I'm literally referencing the periodic table. Now, all of these elements that are listed on the periodic table are atoms. And atoms are the basic building block of matter. A very basic model of the atom is a positively charged nucleus surrounded by electrons. Electrons that can only exist in certain what you might call orbits. So the rules of quantum mechanics dictate that in this first level, only 2 electrons can occupy it. In the second level, 8 electrons can occupy it. Electrons are just negatively charged particles. And so say you have this atom here, and you start packing electrons in these shells of the atom. The shells are nothing more than just an organizing structure for where the electrons can be. And these electrons that exist in the outermost shell of the atom are called valence electrons. And the valence electrons are important because they're the ones that are involved in bonds. For the whole length of my talk presentation, pretty much all you need to worry about are these valence electrons, because they're the only interesting ones. And if I may, the kind of inject another comment on atoms and elements, I think it's sometimes confusing. What's the difference between the two? I would say the difference is in terms of quantity, because atoms refer to these units, these building blocks, these unit building blocks that form matter, and elements just refer to some purity. You have only silicon atoms, then you have silicon as an element. If you have only hydrogen atoms, then you only have hydrogen, that's an element, and so on. So now I want to talk a little bit more about these electrons. So I drew these electrons in the atomic structure, and these have negatively charges. And that's important because all charged particles have the ability to exert forces on other charged particles. It's like gravity. Anything with mass, the sun, the earth, whatever, exerts one force on another. So the sun attracts the earth, and that's what keeps it in orbit. In a similar manner, this electron is able to exert a force on any charged particle in its vicinity. We say that it has an electric field associated with it. So any charged particle that could be somewhere around the electron will feel a force. And that is kind of the heart of why electricity power things, is because electricity is literally the conduction of these electrons. We have a material where electrons can flow and power our devices. Now I'll also talk about something called a photon. And a photon is a particle of light. And you might think, what does that mean, a particle of light? We usually think of light as a wave. So like red light has wavelength maybe around 700 nanometers. A nanometer is 10 to the minus ninth meters. Or, so this would be red light, or blue light would have shorter wavelength. It might be something like 400 or maybe 350 nanometers. But what do we mean by a particle of light? So this actually gets into quantum mechanics, which is the study of very small systems. So what do I mean by quantum? Well, in some ways, when I say quantum, I'm talking about the physics of the very small. This includes photons, it includes electrons, it includes atoms. And what it is a series of rules and laws that dictate how small matter behaves. And one of the most foundational concepts to this is what's called as wave-particle duality. And it means that these quantum particles sometimes behave like finite particles that you know, like pool balls on a table, and sometimes behave like waves, like, you know, the ripples in a water. And to kind of demonstrate this duality, I'll talk about this experiment, this historically relevant experiment called the double slit experiment. And it's where you have a screen, like an opaque wall, and you make two slits in this opaque wall. And you start firing electrons or photons, quantum particles, at the wall. And in another perspective, if you're looking straight down at the wall, you have this wall, and here are the two slits you made. I'll draw them with dotted lines. And you're shooting particles at the two slits. Now, wave-particle duality comes in when you change the spacing of these slits. As long as they're far apart, the quantum particles behave like particles. They'll either go through one slit or the other and be detected on the other side. So you would get a grouping of particles here and a grouping of particles here, as long as the slits are far enough apart. But quantum mechanics means, or tells us, that when you exert these quantum entities to dimensions that are very small, when you bring these slits closer and closer together, they start to behave like waves. So if you imagine splashing water on this side and a wave passing through these two slits, you would get one wave front coming out this slit and another wave front coming out this slit. And you get this interference pattern where the waves add or subtract. And so on the back of this screen that you're waiting and looking for particles, instead of seeing two columns where you get particles coming through one slit or the other, you get essentially a continuous pattern of high and low detection marks of where these waves, at this point, they're behaving like waves. These photons, these electrons go through the slits. They're not acting like particles. They act like waves and show a pattern on the screen rather than just two slits.
Hey, Joe, can I ask you a quick question at this point?
Yeah.
I've watched lots of videos on this, and I've never been able to ask the video producer this question, but you know, you had the arrow there pointing straight. So in my Newtonian world, let's say it was a bullet or an electron. I fired it out of that gun, the electron gun, and it will go straight. So my Newtonian thinking is saying, well, it's just going to hit neither of the, yeah, it's just going to pile up there. How does it, something's changing between the barrel of the gun there and the wall for it to decide to go to both or just one? What am I missing there?
I think you bring up a good point, and from my understanding, the reasoning is that this beam is not perfect, and so there's some statistical variation. That's why they say that you get two equal columns, because you only have two opportunities for the electron to go. It'll either go through one or the other, and as long as the beam is directed somewhere towards the middle, they have equal probabilities. But that the ability of the electron to go not at the center of the wall, but through the two slits is from just, in any practical sort of device that shoots these particles, there's some variation that enables them to go through one slit or the other. And since it's pretty random, that's why they say there's, two lines, because it could, with these random fluctuations, it's either going through one or the other, and it does it equally so.
So the distances here between the slits, first of all, you're the first one that made me aware that the distance between the two slits matters, but we're talking super, super close together here. They're not really, 10 inches apart.
Right, exactly.
Right. Okay. Amir has one quick question in chat. Let me have has any experiment been done when the transition happens from particle to wave as you bring the slits closer?
So actually, this brings up another very peculiar behavior of quantum entities, and that is that the interference pattern, the wave kind of behavior, collapses as soon as we try to observe the experiment in live time. And in reality, why that is because the light that we have to use to shine on the system to kind of observe what's happening during that transition actually affects the particles. So if you try to observe this experiment going from particle behavior to wave behavior, you won't see that transition because the act of observing is causing these systems to exhibit particle behavior. So when they run this experiment and see like a wave interference pattern on the back screen, what has to happen is that you allow the experiment to proceed without observing it. You have some like phosphorescent screen in the back that can detect particles as it hits it, but you're not actively observing with a camera or anything during the experiment, or else that will ruin sort of the wave behavior.
Makes total sense. At the quantum level.
Yeah, totally. If it makes no sense to you, that's the point. It doesn't make any sense.
If it makes no sense, yeah.
And that's why we're here. We're here because quantum makes no sense, and we want to figure out how to use that nonsensical business.
So if it makes sense, you're wrong. If it makes no sense, you're right. You got it.
Exactly. So now I want to mention some fundamental concepts of electricity. And when you talk about electricity, you'll hear words like current and voltage. And what in the world do these mean? Well, talking about electricity, a very useful analogy to make is to water flowing through a pipe. So just like you have electricity flowing through a wire or any other material, you can imagine you have some pipe that is full of water. Imagine that it's not spilling out the sides. It's not going to spill out the side, but you want this water to move. And in order to get it to move, you need to exert some force on the water. Now, gravity provides a very convenient force to use because all you need to do is tilt the pipe and the water will flow. In terms of electricity, current is this flow of water. We tilt the pipe so that water will flow, so that we get electrical current. And voltage is nothing but the tilting of this pipe. So when we talk about conductivity, that means how much flow we get for a given tilting of the pipe. If I tilt the pipe 15 degrees, do I get a lot of water flowing out or a little bit of water flowing out? If it's low conductivity, that means I tilt the pipe some amount and get very little flow. If it's high conductivity, that means I can tilt the pipe the same amount, but I'm getting a lot of flow. And that makes sense. Something that is very conductive, it is easy to get electrons to flow in a material. So when I talk about the conductivity of any material, whether that is, you know, a metal, a semiconductor, whatever it may be. Just think the flow of electrons through that material is easier or harder in some way. And now I want to show you why this concept of conductivity is important. In electrical engineering, we want to build circuits that do useful things. And to do so, we use devices that can interact with our physical world. So on this breadboard here, this is a series of connections that I can make. I can plug in components to this board and connect them into a circuit. So I have some LEDs, some light emitting diodes, and all an LED does that you're probably familiar with is emit light. So I have red LEDs, they will emit red light. And one important thing about conductivity in terms of electrical engineering or building circuits, doing useful things, is that we must be able to control the conductivity of materials. So I have connected here, I'll just draw it in this way, a light and what is called a resistor. And so when I draw these lines, I'm drawing wires. These are literally metal connections that are made to the components, to the LED and to the resistor. Oh, we lost it. We're back. All right, and this resistor. And the resistor is nothing but a piece of material that the manufacturer can decidedly choose what conductivity it has. So it can have low conductivity or it can have high conductivity. And the reason this is important is because the LED can burn out if it gets too much current. And so we need to add a resistor. A resistor has low conductivity so that we tilt the pipes and only so much current can flow through so that the LED doesn't just burn out, it glows at a consistent color. And now here I have connected two sets of these LEDs. One of them on the left has a lower resistance. That means it has higher conductivity than this resistor on the right. The resistor on the right is very resistant, has much high resistance, low conductivity. It resists flow more than that on the left. So I will connect a battery. This is nothing but tilting the pipes so water can flow to this circuit, and it'll be connected to both sides, and we'll be able to see the effect of the difference in conductivities. On the left-hand side, this material has a lower conductivity, so more current, or a higher conductivity, so more current is flowing through it. That gives off more light. On the right, this material has a lower conductivity, so for the same voltage, the same tilting of the pipes, we get less current flowing through this part of the circuit and the light is dimmer. Now that immediately makes being able to control the conductivity of materials very useful. One, it allows us to use things without breaking them. Two, we can control some aspect of these devices. So we can make the LED bright or dim purely depending on how conductive this material is. Just to demonstrate what happens when there's no resistor in this circuit, it won't be very exciting, but you might see it for a second. The LED will just turn on and then it burns out very quickly. That LED is done and it will not work anymore. So in our cell phones or our laptops, we don't only want to operate one LED. You know, we want to operate a touch screen that is composed of, you know, thousands, millions of LEDs. We want to operate a camera. We want to operate a microphone, some speakers. We need to send information and receive information through antennas. And how in the world are we going to do that when in order to turn on a couple of LEDs, we had to take up, I don't know, 2-inch square section of this breadboard. And the way this is achieved is with semiconductors. We need semiconductors because they allow us to build very small circuits. So what is a semiconductor? A semiconductor is nothing but a crystal. And a crystal is just a nice, predictable arrangement of atoms. So most of the circuits in your cell phone are made using a semiconductor crystal called silicon. And if you look at silicon on the periodic table, you'll be able to find that it has 4 valence electrons. So I'll draw this as one silicon atom, and I'll use a different color, with 4 valence electrons. Remember that these are the electrons that we care about. There are other electrons in the silicon atom, but the valence electrons are the ones that we care about because they're involved in bonds. They're the interesting electrons. And so what is the connection between this silicon atom and a silicon crystal lattice? So if you look, here's a picture of silicon crystal. It looks quite alien. You can see that it's got uniform properties. It seems the same throughout. And these properties are predictable because it's a nice, periodic, consistent arrangement of silicon atoms. And what does that look like? So using this same sort of formalism, I can draw what this lattice of silicon atoms might look like. You would just have a nice arrangement of silicon atoms, and they're bonded together. Remember that the bonds happen with these valence electrons. And they enter into covalent bonds. And covalent bonds means nothing but the silicon atoms are sharing their valence electrons together to kind of bind together into this lattice, this crystal structure. And so this basic structure of silicon atoms bonded together is what forms the silicon crystal. And what I'm drawing here is just a 2D representation of it. This is what it looks like in 3D. Each of these balls is a silicon atom. And this same pattern will repeat itself in 3 dimensions. So if you look at any silicon atom, whether it's my 2D representation or this 3D image, you have 1, 2, 3, 4 bonds. You have 1 bond, another bond, 4 bonds to its neighboring silicon atoms. And this is what creates a solid, tangible silicon material. And remember that conductivity, electrical current, is nothing but the flow of electrons. If we want to be able to build circuits with silicon, we need to get electrons that can flow. But all of these electrons that you see in this picture are busy bonding. They can't participate in conducting because they have to stay there to hold the lattice together. And that's a problem. We need to come up with some way that we can get electrons that are in the crystal and free to move. They don't have to participate in bonds. And there's 2 ways that we could go about this. And there's one that happens naturally. This first one is we break bonds. And it sounds like a terrible thing to do, but it's not. It happens at all non-zero temperatures because even at room temperature, there is enough energy in just the physical vibration and movement of the silicon crystal that bonds are being broken. The energy required to break bonds is called the bandgap energy. Remember that the bandgap energy is the energy required to break bonds. And so in talking about semiconductor physics or semiconductor materials in any way, what's often mentioned and referenced is this energy band diagram. And all it is it's literally 2 sets of lines. And this is just a catalog of electrons in the silicon crystal, or any crystal you're talking about. This line represents what's called the valence band. It represents all of these electrons in the crystal that cannot move. This line represents the conduction band. These are all, anything above this line represents the electrons that are able to move. And this is a separate diagram from what I've drawn above here. This is in its own. And these two lines are separated by an energy. They're separated by this bandgap energy, because it requires the bandgap energy to take an electron that is involved in bonds and bring it to the conduction band where it is able to conduct. And you might think, is this really a useful or practical way of creating free electrons that are able to conduct? And not quite, but I'd just like to comment on the scale of things. Because if you have a cube of silicon crystal that measures 1 centimeter on each side, you say that the volume of this cube is 1 centimeter cubed. Even at room temperature, I take this cube of silicon and set it in my living room. Just because of the thermal energy, there will be 10 to the 10 free electrons in this crystal. 10 to the 10 electrons per centimeter cubed. I have 1 centimeter cubed of silicon. There are 10 to the 10 free electrons in there, just from breaking bonds of the thermal energy at room temperature. And you might think, holy shit, that's a lot of electrons. But it's not. In this 1 centimeter cube of silicon crystal, there are about 10 to the 22 atoms, silicon atoms. The number of free electrons is puny in comparison. Just by putting this silicon in room temperature, breaking some bonds, getting 10 to the 10 free electrons is not enough to make a conductive material. In order for this material to conduct, to make circuits, like I showed you with this, in order to make circuits, to get materials that conduct well enough to do useful things, we need something more like 10 to the 16th or maybe even 10 to the 18th free electrons per centimeter cubed. And how do we achieve that? We can't just heat up the crystal more. One, because you don't want to carry around an oven with you whenever you need to use your phone. Two, because the properties of this crystal will be damaged in some detrimental way when we start to heat up the crystal. Yeah, it will create free electrons, but who's to say that won't damage the performance in some other way? And it will. So what do? There's something called doping. And doping is what is practically done to increase the number of free electrons in the crystal. Remember that our goal here is to increase the number of free electrons so that we can conduct electricity in the crystal, and that's it. We just want electrons that can move. And so if we look at the periodic table, what would happen if we substituted silicon with phosphorus? Phosphorus is just to the right of silicon in the periodic table, and what that tells us is that it has 5 valence electrons. So it has the same 4 that silicon has, and then 1. It has an extra valence electron. What would happen if we put phosphorus in this crystal structure? Well, let's try it. We take out a silicon and its 4 valence electrons. We put in a phosphorus. It has 1, 2, 3, 4, 5 valence electrons. And 4 of these are satisfying the bonds of the silicon crystal, but this 5th valence electron is just hanging out. In fact, in all practical situations, it is ready to conduct. This is a free electron. And so let's take a look again at this cube of silicon that has 10 to the 22 silicon atoms in it. Silicon, something like that, silicon. 10 to the 22 silicon atoms in this cube. If we replace 1 in 1 million silicon atoms with phosphorus, we will already create 10 to the 16th free electrons. That is because you take 10 to the 22nd silicon atoms of this crystal, you divide it by 1,000,000, and you get 10 to the 16 atoms that you will choose to replace with phosphorus. And we get 10 to the 16th free electrons. And you can do this with more silicon atoms. You can replace more than 1 in 1,000,000, say 1 in 10 to the 5th or something like that. Then you can increase this number from 10 to the 16th to something like 10 to the 17th, 10 to the 18th, maybe even 10 to the 19th. And that's how you get a piece of silicon that can actually conduct electricity, because we've introduced these electrons that are free to move in the crystal. And that's how it's practically done. This is why it's useful, because we can take this silicon crystal and we can change portions of the lattice, the crystal structure, so that it was replaced with phosphorus and adds mobile electrons that are ready to move through the crystal. And that's how it conducts, is the movement of these extra electrons in the lattice. Now, right now, I'd like to make a note that everything I'm talking about here with electrons applies to something called a hole. And I don't want to talk about holes because I think they're extremely confusing and don't really add much benefit to them. But basically, imagine if instead of adding phosphorus to this lattice, we added boron or something to the left of silicon in the periodic table. Then it would have 1 less valence electron. So instead of having 4 valence electrons, boron has 3. So we get rid of one of these, and there's a missing space here. So it turns out that everything I'm talking about, the conduction of free electrons, actually applies to conduction of these lack of electrons. And this lack of electron is called a hole. It's like an electron, but with positive charge. That's how we treat it. So just keep in mind that everything I'm talking about with electrons in the crystal can be applied to holes, which is just nothing more than the absence of an electron.
Hey, Joseph, got a question for you.
All right.
First of all, this is extremely clear, and I'm afraid to feel that I actually understand what you're saying. I just wouldn't want to take an exam on it, but it's very, very clear. Thank you. Amir's got a question here. When an electron moves through the lattice, does the phosphorus ever lose an electron completely, or is it just bumped and another one takes its place?
So it's actually leaving the phosphorus atom. So there's something called the ionization energy, and that describes how tightly is this extra electron bound to the phosphorus atom. And so in reality, when I talk about having free electrons in the crystal, it's important to note that there must be enough energy that this electron is free from the phosphorus atom. And it turns out that at room temperature, for any atom that is seriously considered for doping, it must be that at room temperature is sufficient energy to release that electron from the phosphorus atom. So it's not just changing place, moving around. Ideally, when there's enough temperature or enough thermal energy, which is typically the case with room temperature, this electron is free from the phosphorus. Does that answer the question?
I think it does.
Hopefully.
It's amazing. Amazing. Who invented all this stuff?
Scientists.
I think something more powerful than scientists invented it. They just discovered it.
True. So now you know about semiconductors and you know why they're useful. They're useful because we can change their conductivity in very effective ways. And I guess to make a note as to why this means we can build smaller electronics, It's because we have methods of changing the conductivity of portions of the crystal very precisely. So if I just have, you know, a wafer of silicon, this is a slab of silicon crystal, and I want to build a circuit on it, there is no problem with modern techniques in building a processor, some sort of computer chip on a piece of silicon that big. And it's because the way we pattern the silicon crystal, that we change some portions of it to have phosphorus atoms, some portion of it to have boron atoms, is very precise. You can use very precise electron beams, beams of atoms shot at the crystal, where we can do this very precisely, and that is why you can build computer chip circuits that are scaled down to such extreme scales. But now I want to talk about quantum wells. How do you use a semiconductor to build a quantum well? Well, at this point, I'd like to introduce you to another semiconductor material, and that is the material that I've been exploring in my own extracurricular research activities, whatnot. That's gallium oxide. So this here is an image of gallium oxide. And what does that mean? What does gallium oxide mean? The chemical structure Ga2O3, gallium oxide. That means it has both gallium and oxygen atoms in the crystal, not just silicon. And here is an image of the gallium oxide crystal structure. And it is significantly more ugly than silicon because it has these red atoms, the oxygen atoms, the blue atoms, which are the gallium atoms, and it involves much more atoms in one repeating unit. This is called the unit cell. This is the basic repeating unit of the crystal. So in this three-dimensional slab of gallium oxide crystal, there's this same pattern that repeats throughout. But the interesting thing about gallium oxide is that we can do something very similar to doping. If we look again at the periodic table and we look at gallium, we look just above it. What would happen if we replaced some of these blue gallium atoms with aluminum atoms? Well, it's in the same column of the periodic table, so it has the same number of valence electrons. It wouldn't change the number of free electrons in the crystal, making it more or less conductive, but it does something else. It turns out, if you remember this trend from chemistry, that as you ascend the periodic table, the elements get more and more electronegative. What does that mean? Electronegativity is pretty much how strongly an atom attracts the electrons of a bond. So if we replace some of these gallium atoms with aluminum, they will kind of pull more strongly in their bond. And what that means, what that ends up affecting is that bandgap energy. Because remember, the bandgap energy is the energy required to break bonds in the crystal. And if we replace it with aluminum, these bonds in a way get stronger because aluminum is more electronegative. It attracts, it kind of pulls harder on the bonds, and the bandgap energy increases. So remember that I drew this diagram, two lines. This was the valence band. This was the conduction band. And it was nothing but a catalog of electrons in the crystal. Everything below this line is involved in bonds it can't conduct. It's in the valence band. And when we supply the bandgap energy, we're able to break some bonds and create free electrons in the conduction band. It's just a catalog. These electrons cannot conduct. These electrons can conduct. We have to add some energy for that to happen. But when we start substituting gallium atoms with aluminum atoms and the bandgap energy increases, this gap starts to get larger compared to, say this is gallium oxide and this is gallium oxide, but say we replaced 15% of the gallium atoms with aluminum, And say in this case, we take gallium oxide, but now we replaced, I don't know, 40% of the gallium atoms with aluminum. This band gap energy increases just because aluminum is more electronegative, and so it gets harder and harder. In a way, it gets harder and harder to break the bonds. Well, how does that form a quantum well? How does that translate to a quantum well? Well, imagine if we had gallium oxide here. I'll say GO, gallium oxide. And we sandwich both sides with some alloy of aluminum gallium oxide. That means we replace some of the gallium atoms with aluminum atoms, and the band gap increases compared to gallium oxide. So I'll say these are AgO, aluminum gallium oxide, which just means that we've replaced some of the gallium atoms with aluminum atoms. And what happens here in the conduction band, and in fact, in gallium oxide, it turns out these line up between the valence bands doesn't actually change all that much, so I can ignore it altogether, which is not generally the case. But in the conduction band, there's this divot. There's this divot where in the middle, it takes a small energy to create free electrons, and on the other side of this, it requires a larger energy to create free electrons. So then I ask you, what happens to an electron sitting in this region? Well, it's confined. It's sitting in this region. It can't get out of this quantum well because it has lower energy than the barriers. Remember that these sets of energies between the band gap energy consists of forbidden region. You can't have an electron in these energies because that's just how it is. But what we formed here is a well that the electron is confined in. And remember that quantum mechanics tells us that when an electron is placed in a space where it gets squished to small dimensions, it starts to behave according to quantum mechanics. So when we make this well, this layer, remember that this is nothing more than a layer of semiconductors where we have gallium oxide in the middle and we have aluminum gallium oxide, some material where we've replaced some of the gallium with aluminum atoms, increasing the band gap energy that gave us this quantum well structure. And so what happens when we start to make this layer thinner and thinner is we form a quantum well. A well that electrons exist in, and since they're confined in small dimensions, they exhibit quantum properties. And one of these properties is that electrons in the well can only exist at certain energy levels. That means, remember that I draw those two lines that represent the valence band and the conduction band. In a way, this is another set of those where they're called subbands. They're bands within the conduction band that say you can only have electrons at this energy or this energy. And they're called eigenstates. That means they're allowed energies. So I'll call this E1, energy 1 that the electron could have, E2, energy 2 that the electron could have. And so the first sort of quantum behavior of this quantum well is that electrons can only exist at certain energies. Now I want to kind of invoke this idea of energetic transitions in here. So if I have an electron in the middle of the well, it will prefer to stay in the ground state, in this lower energy. So say I have an electron in the well. But what happens if I shine light, if I emit photons at the quantum well, and this photon has energy equal to this difference? Let's call this difference delta E, which just means some change in energy that corresponds to this energy minus that energy. It's this difference. Well, then it's capable of moving this electron from the lower state to the higher state, and vice versa. If it's in the higher state, it's capable of bringing it to the bottom state. And so if you're familiar with quantum computing or something like that, we could call this the ground state. In Ket notation, it correspond to 0. If you don't understand what I'm talking about, don't worry. And this state could correspond to the 1 state. And by shining light, we're able to change whether the electron is in the ground state or this excited state. And so you might say that by shining light, we put it in a mixed state of alpha 0 plus beta 1. And this is kind of the other quantum behavior of the well, is that we're able to establish mixed states where electrons in this system are not just at energy 1 or energy 2, they're at some mixture between the two. And that's another aspect of these quantum wells that I wanted to bring up. So now I want to kind of discuss how you use a quantum well to do something useful. And what I want to talk about is quantum well photodetectors. So I'll just write quantum well QW photodetector. And we're pretty much already there in creating a quantum well photodetector. Because think about this case. Think about you sandwich some materials together, aluminum gallium oxide, aluminum gallium oxide, where the bandgap energies are larger than gallium oxide, so you form a quantum well. But say you do it in such a way that you have the lower state energy and the excited state, the next higher energy is right near the top of the well. Well, that means that if you have electrons at this lower energy and you excite them in some way to get to this upper energy, that they are now available for conduction. It's analogous to saying we must add the bandgap energy to silicon in order to create free electrons. This is analogous. It says if we have electrons that are stuck in this well, we have to add this energy difference to get them out. It's like you're standing facing a wall, facing a cliff. There's some amount of altitude you must gain to get over the cliff or out of the well. And the way we add this energy is through light. But not just any light, only light that corresponds to this energy difference. And for that reason, we must use infrared light. Infrared light is not visible to the human eye, but it is everywhere. Anything that is at non-zero temperature, that includes you, it includes me, it includes this whiteboard, these markers, this paper. Everything at non-zero temperature emits infrared light. It gives off radiation. You can think about it as it just gives off heat, but heat in itself is a form of infrared light. And so by designing the shape of this quantum well, we can line up these states in such a way that this energy difference corresponds to a certain type of infrared light. You might say, I want infrared light so that I can see lava at night, or I can see parked cars at night. You can design the spacing of these energy levels by changing the dimensions of the well to target that specific type of light. And so what typically is done is this middle region, the well region, is doped. So we increase the number of free electrons in this region. Most of them reside in this lower state. And when light comes, infrared light comes and shines on the quantum well, it causes some of these electrons to surpass this barrier, get to the top, and they're free electrons that are ready to conduct. So we can apply a voltage difference to this quantum well. Remember that voltage difference is nothing but tilting the pipes. And in this case, it's quite easy to understand just by drawing it. We add a voltage across the quantum well. We've tilted the pipes. And now we have this kind of bank of electrons that are deep confined in the well. we shine light, it excites an electron to the top of the well, and now it's free to move. It's free to move, and we can conduct that electron as current. This is current. And this is called photoconduction. It means we shined light that literally increased the conductivity of this material because we've increased the number of electrons that can participate in conduction. And this is how a quantum well photodetector operates. It's nothing but a system where electrons are confined to certain energies. We've designed the shape of this well such that the second energy is in line with the top of the barrier, such that when we apply voltage to the device and we shine light on the device, we can see the amount of current that comes through changing based on how many photons of light hit the device and create photocurrent that allow photoconduction to occur. And are there any questions at this point? Now, what I'd like to talk about are some of these performance metrics of quantum well photodetectors. Because what ultimately my goal is here is to show you some figures from this paper I published and have you understand what that means. So there are three things I want to talk about. One is dark current. Sounds evil and bad. Two is responsivity. And three is detectivity. And to understand dark current, you have to remember what I told you about there being enough thermal energy at room temperature to break bonds. The same energy that can break bonds in the crystal can actually cause electrons that are in this ground state, this lower state, to excite up into the excited state. And that would increase the amount of current that we collect in the circuit. So through dark current, we're getting more electrons, we're seeing more current flow, but it's not because we're receiving any light. It's because there's enough energy in our environment, enough thermal energy to cause some of these electrons to exist in the higher state. So dark current is a bad thing. You don't want dark current because ideally you want any current that you see to be related to the number of photons, the amount of light that you're trying to detect. And responsivity kind of describes this relationship between light coming in and current coming out. Responsivity is literally the current output, current out, divided by power in, power of light in. So it's literally, if I shine 1 watt of light on the quantum well, how much current do I get? It might be, 1 milliamp per watt. I shine 1 watt of infrared light on the quantum well, and I collect 1 milliamp of current out. But remember that some of this current is not just related to photoconduction, to us shining light and getting free carriers that can conduct, but it's also related to this dark current. And it's related to other mechanisms. You might be trying to detect light of, say, a rocket ship that is taking off. You want to analyze the distribution of heat on that rocket ship, so you're using an infrared photodetector to observe that scene in the infrared. But you might be receiving photons from the person standing next to you, or someone's having a campfire next to you. You might be receiving those photons. You have both dark current that is messing with things, and you have your background, whatever is around you that you're not really interested in. And both of these sources kind of distort this responsivity so that it's not exactly what we're trying to see here. We want to detect light from a particular source, and what detectivity is it takes this responsivity, it accounts for these factors, and it gives you another number that kind of balances it out. There's something called noise equivalent power. And to explain noise equivalent power, well, first maybe I'll free up some space. There's something called noise equivalent power. And remember that before any light comes, we have dark current from the thermal energy of the room that increases the number of free electrons that we conduct. We have the background that adds some sort of photons in the mix that we don't really care about. So you might say there's a baseline current that we're detecting. We're detecting this current. This is from dark current. It's from background, whatever. And there are statistical fluctuations in this. So depending on, the background or the temperature variations of the room, this current might fluctuate. But this is not meaningful information. We just want to know about the photons coming from what we want to detect. So noise equivalent power is the power of light that we must provide such that the current coming out is above this mess, this bullshit. We don't care about anything happening below this line. This is the power required to get above the noise equivalent power. And detectivity is nothing but the inverse of this. So when you have lower noise equivalent power, that essentially means your detector is more capable of detecting sensitive things. It's more sensitive. So the higher detectivity, the better, because that means we are less prone to these sources of noise, these sources of irrelevant information that are around us. Lower detectivity means this noise is so much that our source has to be really strong if we want to get any useful information from it. But high detectivity means our detector is sensitive. We can observe what's going on without too much noise happening. And so now I want to talk about some of these figures that are in my paper. For anyone that's interested, this is the title of the paper. It's a mouthful: Theoretical Investigation of Optical Inter-Subband Transitions and Infrared Photodetection in Aluminum Gallium Oxide quantum well structures. That means nothing but we want to look at some of these quantum wells where it's aluminum gallium oxide, which is this big long formula, AlXGA 1 minus X on either side, and gallium oxide in the middle, such that we form these quantum wells. And we've designed them in such a way that the energy levels of the quantum well are able to contribute to conduction when we shine light. That's what constitutes infrared photodetection. And this is just an investigation. We simulate some of these quantum wells and show what happens. So what happens? Well, first of all, I'll show you this figure, which is called the design space. So this is kind of a showcase of what wavelengths of light we can absorb through this process of excitation from the ground state to a higher state with different well widths, how wide the well is. This might be 2 nanometers. This might be 4 nanometers. This might be 14 nanometers. So we changed the well width, 2 nanometers, 4 nanometers, all the way up to 14 nanometers, and we were able to show that we could absorb wavelengths from about 1 micrometer to 70, maybe even 80 micrometers. And the x-axis of this is the barrier composition, how deep the wells are. So 0% barrier composition means it's just gallium oxide on both sides. 40% means the barriers have 40% aluminum replacing the gallium atoms, so their bandgap energy is larger, and we form a quantum well of this depth. But at 70% composition, this is even more extreme because we've replaced more atoms, more gallium atoms with aluminum. The well is getting deeper. One thing to note is that as the well widens, the spacing of these energy levels gets narrower. So you might have two very widely spaced, you might have two moderately spaced, and then in this case, you would have two very close to each other. And in fact, there are additional energy levels when the well is deep enough. You might have 1, 2, 3, so on and so forth. But we're only interested in those two because that is our design for the infrared photodetector, and we want to show how this kind of structure is able to absorb different types of light just because we're changing the spacing of these energy levels. Remember that light is nothing but energy. And so if we want to excite an electron at a small energy gap, we might need light with smaller energy than here. That means we need energy is inversely proportional to wavelength. So that's why as we get to more wider quantum wells, we're absorbing longer wavelengths, because something with very short wavelength has high energy, something with very long wavelength has lower energy. So that's why when the energy spacing gets narrower, because the wells have widened, we're absorbing longer and longer wavelengths of light. And the next figure I want to show just kind of showcases the selectivity of these structures. This is a plot. These are what are called absorption spectra, and each of these colored lines represents a quantum well of these dimensions. And so obviously, and the x-axis represents wavelengths of light. So when we have a very narrow quantum well, we're absorbing very short wavelengths and nothing else. When we have a moderately thick quantum well, we're absorbing moderate wavelengths and nothing else. Nothing else because only energies that correspond to this difference are absorbed. Only photons with energy around that difference between these two states is absorbed. And you might wonder, why do they broaden? Why are these absorption curves broadening as we get to longer wavelengths? And that is kind of a more involved answer, but I'll tell you right now that it is related to the uncertainty principle. If you're familiar with quantum mechanics, you've heard of the uncertainty principle, which basically states in one way that the more you know about a particle's position, the less you know about its momentum. The same thing applies to some sort of energy structure. The more precisely you know a particle's energy, the less precisely you know about the time it's in that state. So when we get to longer wavelengths, and this is, I hope I'm not losing anyone here, but when you get to longer wavelengths, these energy spacings are narrower. And that means that an electron in this excited state is more strongly attracted to, but there's a more strong attraction between these two states. So it's gonna stay in there a very short time. So when we get an electron into this excited state, it's there for a very specific time. This time gets more and more sharper the narrower the well gets, and that means that our uncertainty in energy increases. So that's a very basic explanation. That's why these curves get broader and broader at longer wavelengths, because the particles, we know more and more about the time they spend in these states, so we know less and less about the energy of these states. These curves start to broaden. In the case of 2 nanometers, it's essentially just one sharp peak, saying that we won't absorb light anywhere but here at, say, one micron. And now I want to show you some of the structures we explored in this paper. There's a deep well and a shallower well. On the x-axis is like an energy. How deep is the well? This one is around 1 electron volts. An electron volt is nothing but some unit of energy that is suitable for this scale. Whereas in this quantum well, the depth of the well is only about 0.2 electron volts. And what does that mean? That means that the energy of light required to excite an electron from this lower state to the higher state is higher in this case than that case. That means that it absorbs shorter wavelengths of light in this quantum well structure than this quantum well structure. And note that we have placed these excited states, the second energy level of the quantum well, close to the top of the barrier, so that these structures can be used as quantum well photodetectors. And also note here something that I just realized I forgot to mention. What are these curves? This purple one and the green one. These are what are called as the electron wave function. So remember that I told you that quantum particles behave as waves when they're confined to small spaces. So in reality, we're not entirely sure where this electron that is in this well will be. We must describe it with a probability distribution that we call a wave function that says when the electron is in this lower energy state, it is more likely to be found in the middle of the well, whereas if it's in the higher energy state, it's more likely to be found at the edges of the well. And this is just another trademark of quantum mechanics, is that we must describe electrons, quantum particles in this system, using a probability distribution of where they could be rather than knowing exactly where they are. And now these are the final figures of the paper that I'd want to show you. And remember that I introduced this concept of detectivity, which pretty much tells us how useful is this detector. Do we have to add a lot of power do we have to have a lot of light power in order to kind of really tell the whole story of what we're trying to detect? Or is the detectivity high? So this is a plot of detectivity versus operating temperature. This is for the short wavelength detector. Remember, that means that the well was very deep. This is for the long wavelength detector. Remember that means that the well was quite shallow. That means that we absorbed longer wavelengths, and here we absorbed shorter wavelengths, because shorter wavelengths correspond to bigger energies that are required to jump this gap. Same thing here, shorter energies because we have a smaller gap to bridge. We need longer wavelength photons, lower energy light to cause this transition to happen. And so what does this tell us looking at this figure? Well, we've plotted other material systems besides gallium oxide, gallium arsenide, indium phosphide, zinc cadmium selenide, all these different materials that have been explored for this purpose. And on the left, we show that these kind of maroon colors are our work. There's some uncertainty with some physical material properties we used, and so that's what these error bars are, is kind of like where it could reasonably be. For the long wavelength detector, we show kind of comparable performance to what's been done before. It's not significantly better, not predicted to be significantly better, and what's more, as the temperature increases, the detectivity tanks. That's why typically these long wavelength quantum well photodetectors have to be operated at low temperatures. Right here, these temperatures are at 77 Kelvin, which is the temperature of liquid helium. So they must be cooled with liquid helium to produce reasonable detectivities, which sounds like a pain and a burden, and it is, but that's typically what has to be done in infrared cameras using this technology. But on the right, what we show is for the short wavelength device, we have high detectivities. They're predictably higher than what anyone has demonstrated with any other material. Gallium oxide shows that it could be much, much better than what has already been demonstrated. And what's more, even at room temperature, 300 Kelvin corresponds to room temperature, we have reasonable detectivity around 10 to the 12th. I'll tell you that in order to have a good detector, you need something on the order of 10 to the 10 to the 14th, somewhere around there, detectivity. And we show that it's possible to achieve high detectivities even at room temperature. What does that mean? That means uncooled detectors. That means you don't need to use liquid helium to achieve high performance. You could do it at room temperature. And why is that? That's because in the short wavelength device, this energy difference is so large that thermal energy at room temperature might want to excite these electrons, but it's not enough to get them into this higher energy. That's just a consequence of having a deeper quantum well. And the exciting thing about gallium oxide is it's one of the few materials that are able to achieve that deep of a quantum well. This is because gallium oxide is called a wide bandgap semiconductor. Wide bandgap. That basically means that the energy required, that does mean the energy required to break bonds in the crystal is quite high compared to something like silicon. And it means there's a lot of room to adjust this energy level. That's why we can achieve such deep wells, is because it's a wide bandgap semiconductor. By alloying it with aluminum, we're able to make the well significantly deep. We're able to access shorter wavelengths than are achieved with conventional materials. And because of this, we're showing that at room temperature, you could achieve performance that is quite impressive, and it's not even required to be cooled to liquid helium, liquid nitrogen temperatures. And now that I've kind of showed you what a quantum well is, what semiconductors are, kind of the useful parameters of a quantum well photodetector, I want to just end with some applications, some notes of applications. Why are these useful? I already kind of alluded to this by saying that infrared light kind of fills our atmosphere. It's pervasive. And because of that, there's kind of, like, in my mind, an endless number of possibilities for applications. One exciting application for short wavelength detectors is for optical communications. These are systems where you can communicate between devices not using electricity through wires, but light traveling through these fiber optic cables. And so a quantum well photodetector that is able to operate at these short wavelengths at room temperature is exciting, because you would be able to receive this information, detect the incoming light, uncooled, and in a material system such as gallium oxide, which has been shown to be maturing quite rapidly. That's important because, like I said, we need very precise control of the material and the fabrication techniques to be able to make useful circuits. That's why silicon is so pervasive in technology, because we really understand it and we really know how to work with it. And the same thing is advancing quite rapidly for gallium oxide. That's why it's exciting for optical communications. The other application I talked about is infrared imaging. So this is an image from NASA engineers. They're holding up here a CPU. And this is an image taken with a quantum well photodetector operating at long wavelengths. That means they've designed it to see thermal imaging, to do thermal imaging quite well. And so you can kind of see these patterns in the CPU where parts of it are hotter than others. And that's just one application, is monitoring maybe electronics while they're in use. Are they heating up? Are they cooling down? What's the story here? So the next series of applications I'd like to talk about are from this paper from 1999. These devices have been around for a long time. Remember that the exciting thing about our results is that we show that this can happen in the short wavelength regime, and it can happen in uncooled environments. But here's an image of the Delta II launch vehicle in flight that has been taken using a quantum well photodetector. Why is this useful? You might imagine something like the Challenger rocket disaster, or something that could potentially happen where there's a leak in the system, the temperature is heating up in one place more than another. You want to monitor what's going on with temperature on this blazing rocket as it enters orbit. So that's one useful application. Now here's another very interesting application. This is from the same paper, and this is a scene in the middle of the night of a wildfire that has recently been put out. On the left is an image taken with visible light. You might take the same image with your iPhone or your digital camera. On the right is one that is taken with a quantum well photodetector. And to show you what this might look like, here's an image from NASA of a quantum well photodetector. It's from the 90s. It's a terrible picture, but this is a quantum well photodetector camera. It has to be big and bulky because they require refrigeration. Remember that these long wavelength detectors require bulky refrigeration equipment to get them at cool temperatures. But something like this took this image. On the left is what you would see with your eyes, complete darkness. But on the right, it shows some of these hot spots that still exist from the fire, even when it is visibly extinguished. So this is important. This is useful for firefighting. You can see where the hot spots are, where it could spark up again, etc. And on that same sort of note, here's a similar comparison of a volcano. This is Mount, here, I'll show you the caption. This is Mount Kilauea volcano in Hawaii. On the left is an image taken with visible light. You would take this with your iPhone, you would see this with your eyes. But on the right is one taken with a quantum well photodetector. Remember, it just has the ability to see in the infrared. And you can see these lava tubes that exist beneath the surface of the volcano. That would be extremely useful for geologists, for scientists studying the volcano, etc. And just as a last note about applications, these cameras work not just with a single quantum well photodetector, but an array of photodetectors. So here is a 650 by 486. That means there are 640 quantum well photodetectors along this dimension and 486 quantum well photodetectors around that dimension, and they cover it in a grid. And just to show you how impressive scaling is achieved with semiconductor materials, this is a quarter. 640 by 486 quantum well photodetectors in a package smaller than a quarter. And so what would happen is this sort of sensor would be put in the camera. You'd have a lens at the front. It would focus the image that you're seeing onto this array, and you would be able to kind of see the same thing in the infrared. And so I hope that by showing you some of these applications, you understand, why quantum well photodetectors are useful, and have kind of understood where they come from, why they're around, and how they relate to semiconductor materials and the very basic kind of premise of quantum mechanics. And I think there were some questions, Terrell. If you might, would you mind reading through any of those?
Sure. What's the difference between a QWP and an infrared camera, or is it one?
So a quantum well infrared photodetector is an infrared camera, but this is just one type of detector. So any infrared camera is based on some sort of detector. So remember that I showed this image of a quantum well photodetector array. Let's see. And it has many different detectors in a grid. But these don't have to be quantum well photodetectors. This could be what are called, I think, I can't remember exactly, bolometers they work off a different mechanism. There could be what are called as PN photodiodes. There could be what are mercury cadmium telluride, or HGCDTE detectors, etc. And the difference between these are the physical mechanism, the complexity level of the devices, and the materials they use. So you might ask then, what is the difference between these other mechanisms and the quantum wells? Well, the quantum wells offer two great things, and maybe even a third. One great thing is that they're quite simple. You literally, like I showed you, you literally just need 3 layers: a large bandgap material, a small bandgap material, and another large bandgap material, and you have a detector. And you might need to create several layers of these to make a practical device, but in terms of simplicity, you just have to be able to make layers upon layers of these materials, and you've got a detector. The other thing that is related to this simplicity is cost. These quantum well photodetectors are very cost effective because they're simple to fabricate and you can scale them very efficiently. And I guess another benefit comes from this image. You might have one sort of detector that can only operate in this region. You might have another detector that operates in this region, so on and so forth. But with quantum well devices, you're able to achieve this whole spectrum in one single material system, one single device structure, and that makes it easier to design devices for a variety of applications. You don't have to change the machinery that you use to fabricate these devices. You don't need to change much other than the dimensions of the quantum well. And the other benefit that came from the wide bandgap semiconductors is that they have the potential to be operated in uncooled environments. So that's the difference between quantum well photodetector and any just general infrared camera, is they might be operating on different technologies.
Any other questions out there? Feel free to unmute your mic. This one's a little bit old, but it's good to ask anyway. So can you give us a quick rundown on how do metals conduct? This goes way back earlier, but in a paragraph or so.
So, like I said, conduction is achieved anytime you have free electrons. And the one fundamental property of metals, or aspect of metals that make them so conductive, so malleable, is that rather than being like a lattice of atoms that are bound together by electrons, they're a lattice of atoms that are bound together by like a sea of electrons. So it's not, no two electrons are obligated to stay in a bond. It's kind of just this mobile sea of electrons. So it's like, if you want to talk about what I brought up in terms of these band diagrams, in a semiconductor, you have the valence band and the conduction band. These guys can't conduct. These electrons can't conduct until they get into the conduction band. But in a metal, you don't have any band gap. It's just a sea of mobile electrons. So all of these electrons can conduct. You don't need to excite them. You don't need to break bonds. They're there in a mobile kind of soup ready to go. And that's why metals are malleable. That's why they bend and stretch. That's why they're such good conductors, is because of that fundamental structure.
Cool. Shannon's asking, can you talk a little about possible application for quantum wells in computer processing?
Yeah, so immediately when you have a device that's able to detect light at these short wavelengths, I talked about optical communications. That also applies to photonics. And this is kind of the idea behind photonics is, can we make electronic circuits, electronic devices, the same sort of thing going on in our computer chips and whatnot, but using light? And so I think if you wanted to extend the concept of quantum wells maybe to computers in the most practical way, I would say they could stand to serve as photonic detectors for circuits that might operate on light instead of electricity. And these have some benefits that you can't achieve with electronic circuits. They might be faster, etc. I think kind of the obvious thing to note here that I think everyone might be wondering about is, could you build a quantum computer using quantum wells? And of course, this is a possibility. In fact, instead of a quantum well where you just have a sandwich of layers, they talk about quantum dots. And we've all heard of quantum dot qubits. This is a quantum dot, quantum bit. And this is the same thing as a quantum well, but it's confined in 3 dimensions. So instead of just a sandwich of layers, you have a sandwich of layers and then something confining it in this dimension too. And those have been explored for quantum computers. And in that case, you get the benefits that we all know of a quantum computer, which, just to state, are that you can compute with units of data that can be in 1 and 0 and some superposition between the two. You have the mechanism of quantum entanglement and how that can enable you to have such concepts as quantum teleportation or other forms of quantum communication. So the quantum well itself is not very seriously considered in that regard. I would say most importantly because of what I talked about with the thermal energy, that even at room temperature, you are exciting some electrons, you're messing things up. They're very sensitive to temperature. That's why for qubit implementations, going off of this question about computers, that's why we seek quantum systems that are very insulated from their external environment in qubit designs, because we don't want them messing up the kind of probability distribution of an electron in the system. So that's what I would say in response to that.
I don't know about you guys, but my quantum well is quite filled right now. I don't know if I could take any more. This has been I'm definitely conducting electricity, no doubt. Yeah, Joseph, this is you clearly know your stuff because you can explain it to novices like myself. So I actually feel like I understood you from start to end. So kudos to you, and congratulations on knowing your stuff and getting a paper out like that. Are you working with the patent office there at University of Utah?
No, I am not.
You probably want to get in touch.
Yeah.
It's pretty impressive.
Thank you, Terrell, and I appreciate the opportunity to speak in front of everyone.
It's all beneficial on our side, man. I put the link to your paper out there, and a side assignment for our folks in the audience. I highly suggest taking a look at the recording of this video and with Joseph's paper by your side, because I saw quite a bit of math in there. Not that we're all math phobic, but I suspect with the foundation that he gave us, we might even be able to accomplish, the holy grail of reading a very technical paper and actually understanding it, which is always a rare treat. So I got the link in the chat for you folks to take a look at that. It's in archives as well. It's actually published. Yeah. So as Amir points out, it's not every day, and I was thinking about this as you were going. It's not every day that the author of a paper gives a good backgrounder like this on the fundamentals to actually understand the paper. Usually, I'm guilty of this too. I just kind of assume everybody knows the fundamentals. So this is really awesome, Joseph. Whew.
Yeah, totally.
Can't wait for your next paper, because you know I'll be calling if I see something out there published. Okay, thank you. We really did a marathon session here, but every minute was extremely valuable and understandable. So that's really awesome. We'll put the recording. Joe, okay to put the recording out there for reviewing again later?
Yeah, totally. That's fine with me.
Sweet. Send a copy to your parents and stuff. So,
Will do.
or your future advisor, actually. He or she would be impressed if you go further in your education, no doubt.
Totally.
Okay, everybody, thank you very much, and especially to you, Joseph. And I'm looking forward to your next paper. And by all means, we're gonna pull you back here again sometime. That was
totally
awesome.
I'll be happy to do so. And thanks to everyone who attended.
Thank you. All right, folks. Have a good, oh, actually, it's only afternoon here, so we got plenty more tonight, by the way, those of you who are regulars, and if not, Doug Fink has a presentation about the ecosystem, which should be a lot less technical than this, but all the same, just as interesting. So watch that. I think it's the Washington Meetup group sponsoring that. Just check Quantum-Appalooza, for the details there. Have a good day, everybody, and thanks again, Joseph.
Yeah, you're welcome. Thank you.
Thank you.
Bye.